Section 4.2 is where we really start to get into math in earnest in this book. So if math is not your favorite thing in the world, please feel free to come into office hours, get extra help, schedule tutoring time, ask me questions through email, whatever you want to do. But make sure that you feel comfortable with this math because we're going to be doing a lot of it as we work our way through this chapter and the next. Now, stoichiometry is actually a fairly direct concept, even though it's got kind of this funny longer name. All this is really saying is that we're going to use balanced chemical equations that we've seen before, and we've seen that whole idea before, and we're going to use those to give us conversion ratios to convert between moles of one substance to moles of another within that equation. So to kind of illustrate this first in a non-chemical way, let's pretend that this is our chemical equation. That to make pizza, we use 1 crust, 5 ounces of sauce, and 2 cups of cheese. And if I put all those things together, I get 1 pizza. So some ratios I can get here that I can use as conversion factors. Something like 1 crust per 1 pizza. Or I can use this the other way. There's 1 pizza for every 1 crust. I can also say that there's 5 ounces of sauce for every 2 cups of cheese. I can write that the other way if I need to cancel out something else. I can say there's 2 cups of sauce for every 5 ounces of sauce. Wait. Oh, 2 cups of cheese. There we go. 2 cups of cheese for every 5 ounces of sauce. So the main idea here is that I can make any comparison I want. 5 to 2, 2 to 5, 1 to 5, 5 to 1, 5 to 1 pizza, 1 to 2 cups of cheese. Whatever I need, I can make that ratio and use it to convert between elements of this equation just by using the coefficients in front of those individual items. So let's do just that. So if I have that equation, I'm going to use it and say, how many pizzas can I make with 20 ounces of sauce? All right, so you probably just said 4, but let's look at it mathematically so we can see how we would do this if these answers weren't so obvious or chemical in nature. So I say 20 ounces of sauce. I am going to use a conversion ratio from here, specifically the 1 pizza, which is I want to get units of pizza, and 5 ounces of sauce, so I want to cancel out ounces of sauce. 20 times 1 over 5, I have 4, and my unit is pizza. Alright, so that's how we calculate this. How many cups of cheese will I need along with those 20 ounces of sauce? Well, again, I start with 20 ounces of sauce. But now I want cups of cheese, so that's what's going to go on top. Cups of cheese. I go up here and I see that there's 2 cups of cheese. I put a 2 there. And how many cups of cheese will I need with the 20 ounces of sauce? Okay. 5 ounces of sauce. That's going to cancel with ounces of sauce. 20 times 2 is 40. Divided by 5, 8. I need 8 cups. Notice I could have gone with the 1 to 2 ratio between the 4 pizzas and the 8 cups as well. It should all work out regardless of which direction you go. Okay, so 20 pizzas. How many crusts did I use? Set it up the same way. Worst Z ever. Times 1 crust. Okay, so the 1 from the balanced equation for every 1 pizza. I ever redeem myself. So 20 crusts. And so it's no different when we're going to use this in a chemical situation. It's just I'm using chemicals, and I'm using moles instead of individual items because individual molecules are too small to really be messing around with or paying attention to. So let's see. If we have a molecular example like 2 octanes, 25 oxygens get together by burning and turn into 16 carbon dioxides and 18 vaporous water molecules, I can start asking questions like, if I burn 10 moles of octane, how many moles of CO2 do I form? I approach this exactly like I did before. I start with what I'm given. I want to cancel that. So I put that on the bottom. I want to get moles of CO2, so that goes on the top. And then I go up to the equation. And I get the coefficients, and I put them in. So 10 times 160 divided by 2, I'm guessing 80, but let's check. Yep, 80 moles of CO2. Okay, so sig fig wise, these ratios are exact. Okay, they're from this equation. The equation is exactly balanced. I don't have to worry about the sig figs here, so I only really worry about the 10. So there's either 1 or 2 here, and depending on what you decide, then that makes 1 or 2 there as well. Alright, if I burn 10 moles of octane, then how many moles of oxygen did I use up? Doesn't matter which sides of the equation that they're on, everything relates to everything else up there. So I want units of moles of O2. I want to get rid of units of octane. So again, 2 for octane. Go up here and find 25 for O2. And we have 10 times 25 divided by 2. 125 moles of O2 form. Now 2 sig figs, we're not really focusing on sig figs here, but 2 sig figs would put this at about 1.2 times 10 to the 2 moles of O2. If you wanted to round up to 1.3, knock yourself out. We don't get too involved in that, where the 5 goes aside of significant figures in this class. Alright, so we've mastered that level of complexity. Let's up the ante a little bit here. If I burn 10 grams of octane, how many moles of CO2 do I form? Well, we've done this problem. The only difference is now this is in grams. But I know how to get moles from grams, because we've practiced that before. I just have to add up this number of carbons, so 8 carbons times 12.01 grams per mole from the periodic table, plus 18 hydrogens times 1.01 grams per mole. So we have 12.01 times 8 plus 18.8. And we get a molecular, or a molar mass, I should say, of 114.26 grams per mole. Not rounding, don't need to round yet. So that allows me to turn this 10 grams of octane into moles of octane. Okay, so 1 mole for every 114.26 grams. It's a conversion. I can use it in any direction I want to. And now we have moles. So 10 divided by 114.26, and we get 0.08752-ish moles of octane. All right, no big deal. Now I can do exactly what I did before. When I had moles, I can use the balanced chemical equation to say if I have this many moles of octane, so octane goes on the bottom because I don't want that unit. How many moles of CO2 do I get? So CO2 goes on the top. I find the coefficients, 16 and 2, and I multiply this out. And I get, in this case, 0.7001-ish moles of CO2. I really can only justify probably at most 2 sig figs. So we're looking at 0.70 moles of CO2 is our final answer. Okay? So this is exactly like what we did before. We just needed one extra step to kind of set it up. Okay, so if I burn 10 moles of octane, I can also ask the question of how many grams of oxygen did I use? Okay, well, we know how to start this out. 10 moles of octane, 8 H18. We can get to moles of oxygen, right? We have to always use moles in this set of ratios. This is not the gram ratio. There's not 16 grams of carbon dioxide for every 18 grams of water. That's completely untrue. They weigh totally different amounts here. But these are the mole ratios to each other. So if I want to get rid of moles of octane, there's 2 in the balanced equation, and I want moles of oxygen, and there's 25 of those. Then, this looks vaguely familiar, doesn't it? I get my 125 moles of oxygen. That's how much I had to use up, but it's asking now for grams, but that's okay. I know how to get from moles to grams and grams to moles. Right? We learned that in the previous chapter. I just have to add up the molecular weight, which is 16 for each oxygen, so the whole weight would be 32.00 grams every mole of O2. So I could just say 32 grams on top, because I want grams of O2 at this point. That's my answer I'm going for. And I want to cancel out moles of O2, so that goes on the bottom. Multiply this out, and I get about 4,000. So the 2 sig figs, you get about 4 kilograms, or 4.0 10 to the 3rd grams of oxygen. Okay? So all we did is add one more step. It could be at the beginning, it could be at the end, but I may have to start with grams, I might have to end with grams. The key factor here is when I go from one substance to another, you better be in moles. Okay? So from one substance to another substance, you must be in moles. The only way these ratios work are in moles. Okay? So don't try and use these ratios with grams. Alright, so let's try one more step more complicated, and then I think we got this, right? We're going to start with our 10 grams of octane, but now we're going to find grams of CO2. Not a big deal, right? We know how to set this up. 10 grams of octane. We can go to moles. Why do we want to go to moles? Because moles will allow us to go from one substance to another. And then once we have the moles of the other, we can go back to grams. So 10 grams times 1 mole of C8H18 for every, well, let's look back at the last slide, every 114 grams 8 carbons and 18 hydrogens worth. Good. So now our units are moles, and grams have canceled out. Now we use this ratio of 16 carbon dioxides for every 2 octanes. Okay, so octanes will cancel out. So now our units are moles of CO2 at this point. So we can get rid of moles of CO2 because we don't want moles, we want grams of CO2. And we just have to figure out the molecular weight. 12.01 grams times 1 carbon, and 16.00 grams times 2 oxygen. So 32, 33, 34, 44.01 grams per mole as the molar mass for carbon dioxide. Alright, so we have 10 moles, and moles cancel. CO2 and CO2 cancels. Actually, we already have the moles down here, so that's that. Just 44.01 grams of carbon dioxide for every 1 mole of carbon dioxide. So 10 divided by 114.26. So at this point we have 0.0875 moles of C8H18. Alright, now times 16 divided by 2. So at this point we now have 0.700 moles of CO2. And now times 44.01 grams for every mole. Now we have, at this point, 30.81 grams of CO2, and we're done, because that's what we were looking for, grams of CO2. That's our answer. So the 2 sig figs, 31 grams of CO2. So the hardest that this can really get at the moment is right here. And the idea that you should keep in mind is if I have grams, I want to bring that up to moles. Once I'm in moles, and I do this with the molecular mass, once I'm at moles, I want to go to moles of whatever it is I'm really interested in. This is from the balanced equation. And then if I want grams again, I just go back down using the molecular mass again, but of the other substance, and I'm back in grams. So there's 4 parts to this, and 4 conversions I could make. If I start at moles and I want to end at moles, 1 step through the balanced equation. If I start at moles and I want to end at grams, fine, moles to moles, using the balanced equation, down to grams. If I start at grams and want to end with moles, I go grams to moles, to molar mass to moles of the other stuff, to the balanced equation, and I'm done. If I have to do this whole craziness where I go all through the steps, grams to moles, moles to moles, moles back to grams. And so this kind of flow chart I found helps us to kind of keep in mind where we're at and where we're going and what steps we need to take along the way to get there. So try this next one, pause it, and now we're back. So 10 grams of octane, C8H18. We want grams of oxygen that we used up. So we're right here right now, and we want to get to here. Can't go directly across, there's no bridge there. We can go to moles, and the moles of the oxygen, and back to grams. So, first step, moles of octane. 1 mole of C8H18 for every 114.26 grams of C8H18. Good. Now, we're going to go from moles to moles. So 25 oxygen, because that's where we want to get to, oxygen. Uh, that many 25 oxygen moles for every 2 moles of C8H18. Okay, good. So now we're over here in moles. Now we want to go back to grams because that's what the answer is asking for. So oxygen, 32.00 grams per mole, that conversion factor. Right, the molar mass, grams of oxygen for every 1 mole of oxygen. And there we go. Moles of oxygen cancel. Moles of octane cancel. Grams of octane cancel. We're left with units of grams of oxygen, which is good because that's exactly what we want. Now we just punch through the numbers. So 10 divided by 114.26 times 25 divided by 2 times 32. And as long as my calculator is not lying to me, that tells me I needed 34.9, so 35 grams of oxygen to exactly burn up 10 grams of octane. That's as hard as it can really get in this section. So as long as you got this, you feel good about it, we're pretty much all set.